todos ustedes. Les invitamos a tomar sus lugares. Vamos a iniciar en un instante. Muy buenos días, bienvenidas, bienvenidos. Y muy buenos días, tengan todas y todos ustedes. En nombre del Instituto Mexicano de Bienvenida, nos da muchísimo gusto estar otra vez reunidos en esta comunidad de conocimiento, de aprendizaje, y esta mañana con un tema de verdad de lo más interesante que tiene que ver con la salud humana, que tiene que ver con el tratamiento de agua para beber, con un método para la eliminación de virus con filtros de cerámica de bajo costo para el tratamiento de agua potable, a cargo de la doctora Mona Soliman. Ella proviene y trabaja en la Universidad de la Tecnología de Delft y le agradecemos muchísimo que haya aceptado esta invitación del Instituto Mexicano de Tecnología del Agua y de la Cátedra UNESCO IMTA a compartir parte de su trabajo y además de la manera magnífica en la que ella lo realiza. Yo quiero darles la más cordial bienvenida a todas las personas que se están sumando y que nos están acompañando en las diferentes plataformas. Nos acompañas a través de esta plataforma Zoom y también te saludamos si nos estás siguiendo desde Facebook Live o también si nos estás siguiendo desde Canal IMTA. Estamos saliendo totalmente en vivo y a la vista en la pantalla tenemos las redes sociales del instituto donde muy probablemente te enteraste de esta invitación y esta convocatoria y donde estaremos compartiendo todo lo que se genere en este espacio de conocimiento, en este seminario de este viernes 8 de abril. Y como todos los eventos de conocimiento que realizamos en línea, esta sesión está siendo grabada, de forma que si necesitas volver a ver el material y la información que comparta la doctora Soliman esta mañana, pues ahí va a estar disponible para todas y para todos ustedes. O si sabes de alguien que por alguna razón no pudo conectarse ahora en vivo, pues puede verlo en cualquier momento en nuestras redes sociales, en los sitios que tenemos en la pantalla. Quiero comentarles también un poquito la dinámica que tendremos durante este seminario y cómo estaremos realizando la misma. Ustedes que se encuentran en la plataforma Zoom habrán notado que de entrada sus micrófonos y sus cámaras están cerradas y así van a permanecer a lo largo de esta parte de la sesión, pues para favorecer una mejor experiencia tanto de nuestro ponente, de nuestro moderador, como de todas y de todos ustedes. Y sin embargo, como la interacción con cada uno de ustedes es muy importante, la forma de establecer comunicación será por escrito a través del chat. Si te encuentras en Zoom, en la parte baja, en el menú inferior, está la ventanita para chat y ahí vamos a estar esperando tus comentarios, tus preguntas, tus intervenciones. En cualquier momento puedes hacerlas a partir de que inicie la charla de la doctora Soliman, y si nos sigues a través de redes sociales, de igual manera, nosotros estaremos muy al pendiente en los espacios de comentarios para ahí estar recibiendo sus preguntas, comentarios, intervenciones a la presentación de esta mañana. Yo quiero comentarles también que para la moderación de esta sesión tenemos también la fortuna y el honor de contar con el doctor Laurent Corti. Él es el coordinador de hidráulica del Instituto Mexicano de Tecnología del Agua y quien tuvo pues mucho que ver en poder concretar esta invitación con la doctora Soliman esta mañana. Y yo saludo con muchísimo gusto entonces a nuestro moderador de esta mañana, el doctor Laurent Corti. Muy buenos días, Laurent, ¿cómo estás? Te saludamos.
Hola, Marco. Buenos días. Muchas gracias. Muy bien. Pues como dijo Marco, yo voy a ser el moderador de esta sesión y pues voy a seguir en inglés para que la doctora Mona nos pueda entender. Thank you very much, Marco. So yeah, I will be your the moderator today, and it's with a great pleasure that we receive the Dr. Mona Soliman, who is an international water expert who works in research and consultancy. She worked as a water engineer and project coordinator for national and international firms. And in 2013, she moved to the Netherlands to start her Master of Science in Urban Water and Sanitation at UNESCO IHE. A thesis on phosphate recovery from wastewater was awarded the best MSc thesis by the Bill and Melinda Gates Foundation. Later, she started a PhD in the Department of Sanitary Engineering at TU Delft. Her PhD research focused on enhancing virus removal in ceramic pot filters. And during her PhD research, she spent time in Nicaragua working on ceramic pot factory and conducting field research in collaboration with local NGOs. And of course, she finished her thesis and she is now a doctor. Congratulations, Mona. And it's a great pleasure to have you today. The microphone is yours, Mona. Thank you very much.
Well, thank you so much for the introduction. Yeah, I'm really happy to be here today, and sorry that I don't speak good Spanish to give it in Spanish. Well, I don't speak any Spanish, but yeah, so the topic that I worked on during my PhD is enhancing virus removal in ceramic pot filters. So through my presentation, I will walk you through some things that were done directly on the ceramic pot and other work that was done on the side to be applied on the ceramic pot filters. So if we start, can you please next? Yeah. So for those who don't know the ceramic pots, the way they are manufactured is the same exact way a pot filter or a flower pot is produced. It's clay and water, so it's very simple to produce. And the clever twist on it is that usually ash is added to the mixture before you produce the pot. Then when they are fired in the clay firing, this ash evaporates and then it creates small pores. And then the water can pass through the filter. So if you press next, and then you can see, yeah, can you press the next one? Yeah, so you see here how the pot itself is used as a filter. You put it on top of a plastic bucket, fill it with water, and the water is filtered down. Press next, please. And then you can see beside it a picture. So this is how it looks like when you see it at your home. The filter sits directly on top of a plastic pot. And this is actually very important because when you filter water, the water is protected inside of this plastic pot, inside of this plastic bucket, and then it remains safe after it's filtered. So we don't want to change anything about the way it works, but we want to make it work better. So if you press next, please. Yeah, so the problem mainly with ceramic pot filter is that when you have water that's not treated or raw water from a river or from any collection point, it has bacteria and it has protozoa and it has viruses. It has harmful microbes. And when you filter that through ceramic pot filter, so press next. Yeah, and press, yeah. So you see here that if you press again, then you will see that usually the bacteria and the protozoa, it remains inside of the filter, but viruses go out. And when viruses go out, they are actually still in the water that's filtered outside of the filter. So they reach the consumer and then they can cause harmful diseases. Press next, please. So why is that happening? Because the pores, the openings of the filter are usually quite big, bigger than the virus size. So the size of the virus is around 20 to 80 nanometer. But the pores of the filter is around 1 micrometer. And although they are small, they are still bigger than the virus, and the virus can pass the filter. Okay, but how much do we need to remove to consider that the water that's filtered is safe? So press next. Yeah, so here you see the WHO recommendation, which basically is described in log reduction value. So to classify any filtration system or any treatment system that it provides a protection to any consumers, then you need to have at least, when it comes to viruses, you need to have at least 3 log reduction values. And how is that calculated? So if you have the amount of viruses that's coming in the water, and you divide that by the amount of viruses that go out in a log value, then you have a certain number. And that number, you need to remove at least 3 logs of viruses from the water to be able to classify any treatment system as a safe treatment system. So where does the ceramic pots fall on that? They don't actually classify as protective or highly protective. They fail completely when it comes to virus removal. So if we go to the next slide, so yeah, this is basically the main problem that we had, that although the ceramic pots are nice and they treat water and they work nicely, they don't remove viruses. Then there was a hypothesis by one of the researchers that if you use the filter to treat water that has nutrients on it, and then you don't clean the filter from the inside a lot, then you will have a biofilm that will grow in the inside of the filter, in the walls of the filter itself. And that biofilm will become very sticky, that when water comes in containing virus particles, they will stick to that biofilm. And then you will have a better removal of virus inside of the filter. Sorry. So the first thing we wanted to do is to check if that's actually happening. If when people use the virus for a long while, use the filter for a long period, you can grow a biofilm inside and then it becomes sticky and then you can remove more virus. So please click next. Yeah, so this is an example of what is a biofilm. So when you have bacteria, the bacteria start to accumulate on each other and then sense that they are around, and then they produce a very sticky material to attach to anything. And that's the basic concept of what is biofilm. So when you have the water coming in, it has bacteria and it has nutrients to grow in, and this bacteria remains on the side of the filter, you will have a growth of biofilm inside of the filter. So press next, please. So this is an example of the experimental setup that we had. 3 sets of filters. One that we filtered through it water that has very low nutrient. So the amount of carbon that was in the water was around 3 milligram per liter. And then the second one had a medium nutrient, around 8 milligram per liter of carbon. And then the third set had 20 milligram per liter of carbon. So those are 3 different sets to see if we continuously filter water. We use those filters for a long time. Will we have better removal of virus and biofilm growth or not? And then we used those, so please click on it. Yeah, so we used them continuously for around 6 months. And what we saw next is, so we saw that there was a biofilm that grew inside of all filters. Press next, please. And depending on the amount of nutrient that was in the water filtered through the filter itself, there was a thicker biofilm. So when you have more nutrient, you had a thicker biofilm, and then there was more removal of virus. So the check that we did was actually correct, that if you are using that filter to filter water that had a lot of carbon or a lot of contamination, you will have a higher removal of virus. But the question is, was that removal enough for those filters to be safe or to be protecting any user from viruses in water? So the answer to that is that you see here, this is the log removal of the virus that we used. So you see for the low nutrient, it wasn't even 1 log. The medium nutrient was 1.6, and even the high nutrient was 2.4. So if you remember from the previous slide, it was we need at least 3 logs to say that those filters are safe for people to use and they are safe against viruses. So even for the high nutrient, that didn't happen. And the other problem, if you click next, then you will see that with the higher removal, the flow rates of the filter went down, which is expected as well, because when you have a sticky biofilm in the filter, then water can't flow through a lot, and then the filters become very slow. So this became a problem. So please go to the next. Then you see here that, after growing the biofilm, we have a low flow rate, and we don't even have a high log reduction values. We don't have even 3 log removal values. So we need a different solution to that. And please go to the next. So we need a different solution to that. And one of the solutions that we tried to check what would happen if we use metal ions to add to the filter to improve virus removal. So go to the next and the next step. So we wanted to check for metal ions and in particular copper and the silver. So go to the next, please. And go to the next, please. So the main goal is to apply copper and silver in ceramic pot filters. But then when we looked at all the work that was done and the research that was done before, there is a lot of things that are not known about copper and silver ions and what they can do when it comes to virus. So if you know any ceramic pot factory, now they actually apply silver to the filters to disinfect E-Coli, to disinfect the bacteria. But when it comes to viruses, there is not knowledge if it can work for viruses or not. Why copper? Because copper is cheaper than silver. So if we can substitute silver with copper, then we give also the ceramic pot factories a cheaper option to protect people from microorganisms and to apply something that can work also for viruses. But we wanted to know, does the virus type, if we have DNA virus in water or RNA virus, does it matter in the disinfection? And the water chemistry, if the pH of the water is different, or if it has NOM, natural organic matter, would it matter how much you will inactivate in the virus? So click next, please. And the last thing was, would it matter if we combine copper and silver? Would they work better, or one of them will work better than the other? So we checked on that in series of experiments. So I will show you in the next one. So here you can see those are images of RNA virus to the left and DNA virus to the right. And this is the way the virus looks under the microscope without any treatment. Then next, you can see when we add silver ions, So you see here that the DNA virus, it basically lost all of its shape. So it lost those spikes and it didn't become round. And this is what we consider that it's inactivated. It can't infect anybody anymore because it became completely different. And to the left side, you can see the RNA virus became very black. It's not even holding in a round shape anymore. It became completely destroyed. So we knew that silver ions can kill both DNA and RNA viruses. And then when we add copper, so you can see here that for the DNA virus, actually the copper ions alone didn't do anything. That's what you see on the right. The particles, the virus particles look exactly the same as before treatment. But for the RNA virus, it's still like very dark from the inside. So it looks like copper can do something to kill the virus, the RNA virus, but not the DNA. So for the first question, does it matter what type of virus is in water? Yes. The same ion will not kill the same different types of virus. It might work for one, but not the other. So if we go to the next point that we had, what is the effect of silver ions, for example, on DNA and RNA virus? And here I will show you the graphs of the effect of water chemistry. So you see here on the y-axis is the amount of log removals. And if you recall, we really want to have around 3 logs, and the time on the x-axis. And what you see is that the pH of the water. So we changed the pH of the water to see if that will affect the inactivation that we will get, how much virus is killed per hour. And you can see for the RNA virus, the silver works for RNA virus and for DNA virus. But for example, for the RNA virus, the more you go to alkaline, the more you go to the water having a higher pH, the more you will get faster inactivation per hour. So at pH 7, for example, you have 2 logs in 1 hour. And the same for the DNA virus. So the water chemistry, even it changing the pH with 1 log from 6 to 7, made quite a difference on how much virus inactivation you would get per hour. So if we go to the next point, for example, okay, that's, let's say, when you change the pH of the water and the water didn't have any organics. And in this set of experiments, it was at pH 7, and we started adding a little bit of organics or having inorganic buffer, and then adding a little bit of organics, and then adding more organics to see how much inactivation of silver you can get over time. So remember that the background here is that we are adding silver, and then we are seeing how much the water chemistry will affect inactivation by silver to the viruses. So you see on the left side, again, the RNA virus. And when the water didn't have any organics, we can't reach 1 log over 6 hours. But then when we had low organics or high organics, sorry, I think that graph had a bit of a problem. But anyway, so there is an effect of the organic itself. But with the silver, there was not much a difference between low and the high organics. But then when we move to the copper inactivation, so can you please go to the next one? Yeah, and please click on it next. Yeah. So here I wanted to show you, for example, the inactivation by copper when we didn't have any organics in the water. You see to the right, the DNA virus, if you recall also from the images, that the copper by itself didn't do anything to disinfect the DNA virus. So you see the figure kind of flat, there is no inactivation. But for the RNA, we had almost more than 1 log over 6 hours. And then when we increase the organics in the water, you see much higher effect on the RNA virus. So the more you increase the organics in the water, the higher inactivation you will get, which means the faster you kill virus over time. So overall, with any chemical interaction between metals, copper or silver, and the virus, it's a time dependent. The more time the water is interacting with that metal, the higher inactivation you are getting over time. But why, for example, it matters if you have high organics or low organics, and why, for example, it have lower inactivation when you have no organics. So when we looked at that, if you go to the next one, you can see that there is a series of interactions that happens. So when you have copper in the water, copper is a transition metal. So copper can interact with the reducing moieties of any organics. And when it does this interaction, it gets reduced to copper 1. And the copper one in general for the aquatic species, it's more toxic. So it has more toxicity than copper 2. But then copper 1 can interact also with the oxygen and produce something called superoxide. Superoxide is known to be a reactive oxygen species. And for those who are not familiar what are reactive oxygen species, they are toxic forms of oxygen compounds that can actually kill viruses much faster. And that's the reason why when you have organics in water in combination with copper, you get faster inactivation than when you don't have organics. So these interactions keep going, and you have, for example, in the last row, you have production of hydrogen peroxide. And this is also causes a higher inactivation of virus when it's present in water. So to sum up, again, when we looked at the copper and the silver, we saw that there is an effect of which type of virus you have present in the water. There is an effect of the water chemistry. The pH of the water has effect on how much inactivation you can get, and the inactivation of the virus is sensitive to changing the pH. There is an effect of the natural organic matter, and that's a quite positive effect because most disinfectants work less when you have organics. But in that case, they work actually better when you have organics. And there was one more question left. Is it better to use copper and silver combined, or is it better to use one or the other? So in the next slide, you can see that we compared. So in the x-axis, this is the slope, like how much per hour is inactivated. And on the y-axis is the conditions. So the black column is what we see when we have copper and silver combined in water together. And on the column that's a bit lighter, this is what we got from copper and what we got from silver as a sum up, as a mathematical sum up. So you can see, for example, for the RNA virus, the one to the left, that when we had no organics in the water, there was what we call it synergy. So when you add the two metals together to water, they work much better than if you have both of them in different waters, let's say. So they have an added effect, a synergetic effect that becomes way too powerful. And that goes on for the low organics as well. But for the DNA virus, when you have low organics or high organics, this effect becomes very strong. So it's much better for us to use copper and silver combined than using one or the other. I know it's a little bit difficult figure to understand fast, but the main message behind it, if you click next, is that, I wanted to sum up can you click next, please? Yeah, so this is the main message that I wanted to give you from it. So if you have low or no organics, and by low organics, I meant what we checked was around 2 milligrams per liter of carbon in water. So the water was pretty clean. Then, you can have better copper and silver together. But when you have high organics, if you see the last row, then you have a trait. If you want to focus on inactivating RNA viruses, which is the main viruses in water, then using the copper alone will be actually better and more efficient than copper and silver. But if you want to focus on DNA viruses, then copper and silver together will be better. And of course, we can't select which viruses will be present in water. So in that sense, it always depends about how much money is being invested, and maybe better to just apply copper because it can be cheaper and it can be easier to apply. Then we moved to the last stage to try and actually apply them in the filter to see, okay, what would happen when we apply the metals in the common way that the factory uses in the ceramic pot. So those are pictures from the factory where they teached me how they apply now silver to the ceramic pots. So usually they get the ion solution in something, and then they are painted with a paint brush to the filter itself. So can you go to the next one? Yeah, so you see here, it's just like painted or smeared to the filters that are already produced. So if you go to the next one, yeah. So after we painted copper and silver in the same way the filter does, what you see here on the y-axis is the amount of copper that comes out in the water that's being filtered. So we painted the ceramic pots, started loading them with water, and you see that almost 9 grams is coming out of the water. It goes down super fast. So this is the pore volume, like how much water the filter retains. So you can see how much the metals just leach out of the filter super fast, and especially copper. So over 9 grams were coming in the beginning, and that kept coming, and it just went down super fast. So all the metals that we paint the filter with, they pretty much go out in water quite fast. So this is not a good way to apply the metals to the filter. And this is not a good way to also basically invest money in the metals themselves. You're just going to lose money on it, and it's not being retained in the filter. So the last thing I wanted to mention is that also with this problem, when we started collecting water from the filter directly and measuring the log removals, we can see that it wasn't even 1 log. And why is that? Because the filter has very little metal ions left on it, and the contact time between the filter, between the water that contains the virus and the filter till the water is filtered out is quite small. And that also made it clear that one thing is important, that for us to use metals such as copper and silver, they need to be applied in the receptacle of the water itself. So you have a higher contact time and a longer contact between the virus and the metals that are in the receptacle. So if you take home messages, if you can just go to the next one. Yeah. So if you recall, we started from the biofilm growth, and biofilms in ceramic pot filters, they will grow and they will provide a little bit of protection, but this protection will not be enough to make the ceramic pots protective from viruses for any consumer. The second thing is that copper and silver can be a cheap alternative, and they can help protect from viruses, but you need hours of interaction. So you need a post-treatment or a way to apply it that doesn't rely on a small contact time with the filter itself. And we need, if you want to apply to the filter, then we need more research on how we can retain the metals inside of the filter without having them painted and flushed out very fast. Copper and silver can also be applied, for example, to storage water, or if you have systems that have rainwater harvesting, then it can be a way to apply copper and silver there, because you have longer contact time in hours, and it can help you provide safe drinking water in a low cost. And that's the end of my presentation. I would love to hear your questions, and I hope it was clear.
Thank you very much, Mona. Thank you. We have some questions here in the chat. There's one question from Olga Sochi that asks if those addition of metal to the water, does it change the taste of the water? Do you have any information on that?
Yeah, so the WHO has, the World Health Organization, they have a recommendation on how much metals can be added. So the recommendation is that what ends up in the water should be around 0.1 milligram per liter of silver and not more than 1 milligram per liter of copper. They don't change the taste of the water. If you will use them in this way, they are not part of the hardness of the water. But copper, if it has higher concentration, it can cause stomach issues, so you can get sick. And the silver, if it has higher concentration, it's also problematic. It can cause diseases. So in the study itself, we try to comply with what the WHO recommends. So if you stick with that, it should be fine. And currently silver is added to the filter. And I don't think there are, like, people are complaining about the taste of the water or anything. So in the WHO limit, I don't think it can be a problem.
Thank you very much, Mona. Julia Prince is asking, do you consider this filter could work well with groundwater? And do they remove also the organic matter?
So groundwater usually has more problem with arsenic. So it depends on the region where you are having groundwater. And of course, you can use it for groundwater. It wouldn't be, but it depends on what is the problem and what is the region that you are using the filter in. So what I saw in Nicaragua, that people are using it for groundwater. Groundwater usually is more biologically safe than surface water. So you have less viruses, you have less E-Coli in there. But that's if the groundwater is well protected. If you have groundwater that's contaminated, then yeah, of course you have the same issues and you can use the filter for. Does the filter remove organics? My answer is no. It's not made to remove organics. Maybe it will retain a small amount of it, but the filter itself, no, it doesn't really remove.
Thank you. There's another question from Julia. She asks if those ceramic pot filter can be used to remove other contaminants like heavy metals or fluoride.
I think there was studies on that. But for example, if you think about the figures that I showed you in the end about the attachment of copper to the ceramic pots, they don't really do well. They can't really attach those metals. So just even by thinking about it, I haven't done experimental work to see if they do remove well. But just thinking about it, I don't think they are the system for that. They will do very poorly. They will do bad because their attachment to the heavy metal is not something good. It will go out once you start loading the filter with water. It will go out with the water again. So no.
Okay, thank you. We have a question from Jorge Antonio Silencio Gil, who asks if you had any, how do you know if the factory managed to standardize the size of the pores in the filters? How is this?
They are not standard. So there are many studies that looked at the size of the pores in the filter, and they vary quite a lot. We have talked with factories multiple times, but you have to keep in mind that there are, for example, ceramic candles. They are more industrially produced. So they have more control over how uniform the pores are, that you get the same size of the pores in different areas, but they become more expensive and you have to get them from outside of the local sources. I think there are factories in India or in different areas that produce them in bulk. The thing with ceramic pot filters, for example, that they are produced locally. So always you have a trade between the price that you pay, how much you can afford, and the quality that you will get. Do they help in protecting from E. coli, from any water-borne diseases. Yes, and there are studies that evaluated that, and they do protect people. Are they the best option out there? I don't think so. But keep in mind, for example, if you have people that don't have any treatment system, and if you get them, for example, chlorine tablets, then they need to add the tablet to every bucket of water. It becomes a lot of work. Then they are not going to use it in the end. So there are studies that looked at how much people accept the technology and all of that. And the ceramic pot filters is one of those small systems that people use over long time, because you just put it there, fill it with water, and it filters, and it's much easier to use. So is it the best that's out there? No. But is it going to be around for long? Yes, because there are so many advantages, maybe not technical ones, but practical ones that go with it. So that the answer to the board thing, no, they are not uniform, and they are not, the production of them is not very controlled. And overall, there is not high interest to control that, because then it becomes an expensive production process.
Thank you very much, Mon. And this leads to another question that I had in Jorge as well, is this production of a biofilm inside the filter, does this create any health problem, or is there an issue with the growth of the biofilm inside the filter?
Yeah, so biofilms in general, they can, in the same way, if you think about it, that they will retain the virus inside, they can also retain E. coli, and yeah, they can cause a health problem. But the point is, we didn't grow them intentionally. We just filtered the water, and they will grow naturally. And from the field work that I did in Nicaragua, I didn't put it here, sorry, but when we swabbed the inside of the filters from people's houses, the samples that I got, there was a biofilm inside. So all the filters in use will have biofilm. Just put your hand inside and feel the filter. If it's sticky, you have a biofilm. You definitely have a biofilm. So in anything that you use, if you actually feel it and it's sticky, that's clear enough that you have a biofilm. Is it bad? Is it good? From the studies that I did, what we saw is that the biofilm remains inside of the filter and it doesn't grow on the outside. So it's actually okay, because the filter itself will block the bacteria from reaching outside. So if there is bacteria growing inside, it's not gonna reach a lot outside. So you are not like creating a place where you are growing E. coli or growing harmful things and then sending them to people outside. It's not really, at least is not very much the case that I saw with ceramic pot filters. And well, people really brush the inside of the filter and they clean them. But yeah, to sum up, yeah, they grow inside in reality. It's not like we try to force grow them. They grow in every filter. We just try to see, okay, after they grow, what does happen? And do they help improve the filter or not?
Okay, yeah, that's an interesting discussion, because I've read kind of controversy about filters, that people that have filters at home for water, and some people said, yeah, it's good to have a filter, but you have to switch the cartridge or everything, because the filter itself, it's a growth medium for potential harmful bacteria. But yeah, if the bacteria stays on the right side of the filter, then it should not be an issue. Is that what you're saying?
It shouldn't be, no. What I mean is, in a certain magnitude, maybe the filter will be able to block it out, but the filter has a certain removal capacity. So of course, it's not like to enable that, oh, grow it as much as it can. Not like that. It will reach you at a certain point. There are systems that rely completely on biofilms. So slow sand filters, the core of the treatment system is a biofilm. So it's not, but slow sand filters are quite big. You have over 1 meter for this water to reach the outside, and the biofilm is usually in the very top few centimeters. So what I was trying to say is that you can't judge in the water treatment systems, especially the ones that go biological, that biofilms should never happen there. It always depends on what is the protection under that biofilm. So in the ones with the cartridge, what happens is that, when you have the biofilm outside, it's interacting with the water being filtered. So you really need to take it out and put a new one. What I said is that, it grow inside. So you had a bit of protection. But it's not really, and people clean the inside of the filter anyway regularly. So it should be with the cleaning advice and with all of that. It shouldn't be the main worrying thing in ceramic pot filters.
Okay, thank you very much. There's another question about from Jose Di Garcia about commercialization, and he takes the example in Mexico where filters need to conform to some standards and normativities to have the right to commercialize a filter in some market. Do you have any information on, for example, in your work in Nicaragua, those ceramic pot filter were conforming to some legislation or to some normativity or standard? And do you think this could be an issue for commercializing this type of treatment systems?
Well, they are actually quite in use, not just in Nicaragua. I think there are in 35 countries that they are being used. There are also many factories in Ghana. I don't have a very clear info over the local regulations, because those are per country varies. So the WHO considers they have studies and they have things that recognize the ceramic pot filters. So if you even just go to the site of the World Health Organization, you will find so much details about that. If you would like, I can also put you in touch with the factory in Nicaragua, with the management there, and then maybe you can have a chat with them, ask about any details that you need to learn. But I mean, I haven't set up the factory or applied for the license, so I don't really have this info. But I would be happy to put you in touch, or to put the person who's interested to know a little bit more in touch with someone there that can help them know how does it work in terms of legalization, or even setting up the facility or things like that.
Okay, thank you very much, Mona. There are many congratulations for your talk in all the different social networks, and it was very, very interesting. Thank you very much. I have one last question that I think you already answered somehow. Is that so? You said that putting copper or silver ions in the water helps with virus removal, but so does chlorine, right? What would be the advantage of using copper or silver instead of chlorine? So
the problem with chlorine is that it has carcinogenic byproducts, so it causes cancer. So when you put it in the water and it has organics, the chlorine usually interacts with the organics and produces byproducts that are very known. And those, they cause cancer. So that's why if you have, like, let's say, a supply system at home and the water is chlorinated and everything, usually you get like this 3-stage filter with activated carbon or something to take out the byproducts of the chlorine. And that's quite problematic. So that's why we were looking for alternatives that doesn't have byproducts. And copper and silver, they don't have that. They don't produce byproducts. So that's an advantage for them. So yeah, in that sense, another thing is that Also, chlorine usually works less when you have organics in water. So the efficiency that you get of it is lowered by organics. Meanwhile, for copper, for example, it's much better when you have the organics. So having the organics of water makes the copper work even better, not worse. So it has its own advantage in that sense.
Thank you very much. Very clear answer. Well, Mona, thank you very much for the presentation. It was very, very interesting, even for myself, who is not a specialist of water treatment. Very, very enlightening. Thank you very much. Very clear. There's no more question in the from the audience, so I will give back I don't know if you have any last comment to give.
I think my thesis is also available online because it's open access. So if somebody wants to learn a bit more about what was done, because of course I walked through so many things fast, then you can just download it from the website of TU Delft, and then you have all the work that was done. And and for the comment that was related to the factory and the legalization, you can always reach out, and I can ask the people and put you in touch with them if there is an interest in them.
Thank you very much. If you have the link for the thesis, it would be great.
Yeah, of course, I will send it to you.
Thank you very much. So I will thank you very much again, Mona, and I will give back the microphone to Marco. Thank you.
Muchas gracias, Laurent. Thank you very much, Mona, for this great talk with Joy. And we are going to be in touch with you through your social network. So it is very interesting. Yo quiero animar a todos los asistentes también a que pues conecten también con la doctora Mona Soliman en sus redes sociales. Su cuenta, por ejemplo, de LinkedIn tiene un resumen bien interesante de los trabajos, de parte de los trabajos que nos ha comentado ahora. Entonces, de verdad que muy, muy recomendable conocer más de la producción científica y tecnológica de la doctora Mona Soliman. Muchísimas gracias, Mona. Thank you very much again. Y muchas gracias, Laurent, también por este trabajo de moderación bien, bien importante.
No, de nada.
Y por hacer posible también conectar con la doctora Mona Soliman y poder tener pues próximamente también oportunidad de volver a invitar a nuevos espacios de conocimiento y particularmente en este tema de hoy que pues sin duda un tema de lo más relevante ahora que siempre estamos sensibilizados con la salud humana, pero en particular en los tiempos actuales y entre los nuevos retos, pues sí, tener estas alternativas de la aplicación de la ciencia para la preservación de la salud humana a través del agua que consumimos, pues es de verdad un trabajo muy importante, invaluable, y esperamos que esta tecnología tenga pues un espacio para tener su aplicación en muchos lugares de nuestro planeta que lo necesitamos. Muchísimas gracias, y yo quiero invitarles para ir cerrando este seminario a todas y a todos los que nos están acompañando, si tienen oportunidad de encender sus cámaras y si así lo desean, para que podamos tomar nuestra tradicional fotografía, nuestra imagen de grupo para pues celebrar, para dejar una constancia importante de esta comunidad de conocimiento que conformamos hoy. Vamos a permitir ahora que vayamos abriendo nuestras cámaras, todas y todos, y poder ver sus rostros. De viernes empieza el fin de semana, muy, muy importante. Y yo quiero, mientras encendemos todas nuestras cámaras, aprovechar unos instantes para hacerles algunas invitaciones también a actividades y a más espacios de conocimiento que tendremos en el Instituto Mexicano de Tecnología del Agua. Podemos ver la siguiente, por favor. Queremos invitarles a los procesos de educación continua que ofrece el Instituto Mexicano de Tecnología del Agua. Próximamente, del 16 al 20 de mayo, el curso Bases y Aplicación del Modelo WRF. Este estará a cargo de la doctora Pamela Iskra Mejía, el doctor Víctor Kevin Contreras y el doctor Indalecio Mendoza. Importante que entres en contacto si estás interesado en estos temas de modelación, que conectes con nuestro sitio de educación continua. Tenemos los datos de contacto en pantalla, está el correo, el sitio web, y ahí están todos los detalles para tu inscripción, o si sabes de alguien interesado o interesada, pues compartir la información. Te agradeceríamos muchísimo. La que sigue, por favor. Otra invitación es a Buenas Prácticas de Laboratorio, un curso que ha sido de verdad importante para aplicar estas técnicas de laboratorios, precisamente también en materias de calidad del agua. a cargo de Minerva Sánchez. Este curso es del 6 al 8 de junio. Tenemos algo de tiempo para poder concretar nuestra participación. El registro ya está abierto. Igual las inscripciones en el sitio de Educación Continua del Instituto Mexicano de Tecnología del Agua, y tenemos también ahí nuestro correo electrónico para compartirles y que tengan ahí todos los datos. La que sigue, por favor. Queremos invitarles también a que nos sigan y se suscriban a nuestro boletín informativo de divulgación Hidrófilos, esta semana Agua y Juventud, y que tiene pues varias buenas noticias. Estamos regresando a tener visitas guiadas a estudiantes en el Instituto Mexicano de Tecnología del Agua, lo cual nos tiene muy contentos para poder compartir con estudiantes y con todos los interesados de conocer el quehacer científico y tecnológico que tenemos en el instituto. Están ya abiertas este registro para las visitas, está en la página institucional, y también tenemos una sorpresa para todas y todos ustedes. Tenemos un video sobre la elaboración del mural comunitario que se realizó hace algunas semanas a cargo de la comunidad wixárika que nos acompaña en este proyecto multicultural que tenemos para el cuidado y la preservación del agua, un mural precioso que tenemos en el Instituto Mexicano de Tecnología del Agua, y ellos nos cuentan cuál es el significado que tiene este mural, y está el video para que lo vean todas y todos ustedes. De verdad que véanlo, compártanlo, porque es un material bien, bien interesante. Y por supuesto también el regreso a clases presenciales en nuestros posgrados ha sido un tema muy importante para nosotros, el poder estar otra vez poco a poco y paulatinamente, como nos lo permitan las circunstancias, reunidos otra vez de forma física, además de, por supuesto, aprovechar estos medios digitales para poder estar en contacto, por ejemplo, como fue la doctora Mona Soliman esta mañana. La que sigue, por favor. Y les invitamos también, por supuesto, a leernos en nuestra columna semanal Perspectivas, donde tenemos temas de análisis de los aspectos fundamentales en la gestión y el manejo del agua. Esta semana, una reflexión sobre el nuevo Código de Aguas de Chile, bien interesante, que dieron un golpe de timón hacia la Rectoría del Estado, el cuidado de la vida y el cuidado de los derechos humanos en una nueva ley o Código de Aguas de Chile. De verdad, bien, bien interesante. Les invito a leerlo, a comentarlo y, por supuesto, a que nos propongan nuevos temas de reflexión para compartir con todas y con todos ustedes. La que sigue, por favor. Y recordarles, por supuesto, que estamos muy al pendiente de sus comentarios y de sus sugerencias en nuestras redes sociales, y pedirles e invitarles a que estén muy pendientes de ellas también para poder tener la información de todo lo que está ocurriendo en el instituto, en el sector agua y, por supuesto, de los espacios de conocimiento que estaremos compartiendo con todas y con todos ustedes en los próximos días. Creo que esta ya es la última diapositiva y estamos ahora sí listos para poder regresar a hacer nuestra toma fotográfica conmemorativa de este espacio de conocimiento del 8 de abril de 2022, agradeciendo a todos muchísimo. Muchas gracias, doctora Mona Soliman. Thank you very much again for your great talk. Y pues yo creo que no falto a la verdad de agradecerle a la doctora en nombre de todas y de todos los que tuvimos oportunidad de escuchar esta magnífica charla. Y entonces, ¿qué les parece si a la cuenta de 3, pues nos regalamos una gran sonrisa para que quede esto registrado en nuestro historial de espacios de conocimiento, invitándoles a que tengan el mejor de los fines de semana y que sigamos conectados, que sigamos en contacto en esta comunidad de conocimiento que no solamente se mantiene, sino que va creciendo día con día en torno a uno de los elementos más importantes de nuestro planeta, el agua. Muchísimas gracias, que tengan de verdad la mejor de las tardes y el mejor fin de semana. Nos vemos en el próximo espacio de conocimiento. A la cuenta de 3 nos regalamos esta gran sonrisa y nos despedimos. Muchísimas gracias a todas y a todos. Muchas gracias.